to welcome Oscar Bandtlow, who will be talking about spectral approximation of evolution operator using the DMD. Yeah, thank you.
Well, thank you very much, Boumediene. It's a great pleasure to be at this August seminar. Last time I gave this a seminar at Imperial, I think 4 years ago, and I talked about something again related to the particular setup I'm going to talk about now. So basically, the talk is about our recent interest in this machine called DMD, dynamic mode decomposition, or extended dynamic mode decomposition, about which I know very little. And since there are a lot of experts in the audience, I already make this waiver. I say, sorry, I claim ignorance. Everything I say, don't. However, we got interested in it as a tool to approximate spectra of Frobenius, Perron, and Koopman operators. And here is how far our attempts have gone. So I'm going to talk about a particular setup of dynamical systems, very, very simple, very, very narrow setup. However, it's good enough for us so that we can make quantitative statements about the procedure I'm going to talk about. So without any further ado, let me jump into the first slide. Let me see whether I can do it. Yes, perfect. Okay, so the first thing, I'm going to explain the setup. So the interest is in the broadest possible sense. Imagine we have a map defined on some phase space. Let's call it curly X. And this you can imagine to be an interval or a manifold or whatever. In fact, for most of the talk, it will be the unit circle, but for the moment we can keep it general. And on it, I suppose I have a transformation, which I assume to be on the chaotic end. So for me, what does it mean? It means that it's sort of either piecewise monotonic and expanding or hyperbolic. And it also has to have some smoothness assumption in order for the machinery I'm going to present to you to work. So in this particular setup, if you have a map on some compact manifold or an interval, and if the map is expanding, then as you probably know, the trajectories of this system can become very, very complicated, and it exhibits some sort of chaotic behavior. And if you want to tame the description of this very, very complicated description, then what you can do is you can adopt a probabilistic viewpoint and you fix your favorite reference measure, for example, the Beck measure, because this is the one you understand. And then you study the statistical long-term behavior of the iterates of the map tau. Okay, so this is a well-defined, well, this is a sort of a very ancient question, and many, many, many tools have been developed to answer this to a certain extent. And with this setup, there are two operators that allow you to say something about the probabilistic description of this of the iterates of this map. One is called the Copan Operator, and what does that do? It takes a bounded, essentially bounded function on X and spits out G composed with the map. Okay, so if you take the viewpoint of looking at the evolution of observables, then the Copan operator is your tool. If, on the other hand, you are interested in the behavior of statistical ensembles, then a dual object, often known as transfer operator or Frobenius-Perron operator, is the tool you want to look at. And this is defined by duality as follows. So you can show that there's a unique operator L that satisfies this equation here for all integrable f and all essentially bounded G. And what does this operator do is it describes the evolution of probability densities under the action of the map. So in a sense, these two objects describe the same thing. They are devoted to studying the probabilistic behavior of a map. However, from the perspective I come from, this operator, the transfer operator, is the much nicer object. In particular, if tau is an expanding map, then the transfer operator is typically much nicer than the Koopman operator. And this is the reason why most of the machinery in this setup, in the non-invertible expanding setup has focused on the transfer operator. More recently, there's a lot of talk about Copan operators. In fact, people now talk about Koopmanism. People have rediscovered this operator and use it to say a lot of things about Tor. For me, the primary object is the transfer operator, but I'll comment on the relations between the two of them. Okay, good. So this is fairly well known, perhaps. And let me now say a little bit more about spectral properties. So this is a terrible slide containing lots of information. Let me try and walk you through, nevertheless. So the first thing is that the spectrum of the transfer operator is usually not interesting. And what does this mean? Not interesting means the spectrum of the transfer operator on the space L1, on which it's naturally defined because it describes the evolution of probability densities, is either the unit disk in the non-invertible case, or is a subset of the unit circle. Typically, it is the unit circle in the chaotic sense. So you could say the spectrum is not very interesting. And this is why people in my community do something slightly different. They cheat. They look at typically a smaller space, let's call it H, and there's a whole philosophy and a whole tricks, a war chest of tricks and tools that allow you to create these spaces and study their spectral properties. In the best possible setup, in the setup I'm going to talk about in some more detail, you can find spaces H with the property that the transfer operator leaves the space invariant, and the operator is on top of this compact. Okay, so compact, what does it mean? It's a nice possible thing you can have in infinite dimensions. It's an operator that is as close as possible to a finite rank operator without itself being a finite rank operator. In particular, it means that the spectrum of this operator is a discrete set of eigenvalues of the operator with a possible accumulation point at 0. And for later usage, I'm going to follow the convention that my eigenvalues lambda are ordered according to decreasing modulus. And so this is something I already said. Typically, H is a dense subspace which carries a topology that is stronger than the one induced by L1. And if you wonder what this is, you're going to see examples shortly when I'm going to specialize to analytic expanding circle maps. Now you wonder, obviously it looks as if the spectrum of L restricted to H is somehow, there's some arbitrariness to this, but you can show that in a certain natural setups, if you change your space H, then the spectrum does not change. Okay, so to a certain extent, these eigenvalues over here have some intrinsic meaning, and sometimes they're called Ruelle resonances. In the discrete setup over flows, they're called polycot Ruelle resonances. And why do people get excited about this? Because these Ruelle resonances, that is, these eigenvalues of the transfer operator, when restricted to the suitable densely embedded subspace of L1, provides insight into finer details of the decay of correlation functions. So 1 in the setup is always an eigenvalue, and the second eigenvalue typically describes the rate of decay of correlation functions, or if the system is not mixing, then the eigenvalues on the unit circles tell you something about ergodic properties of the underlying map. So spectral properties of the transfer operator tell you something about ergodic properties of the underlying map. Okay, now let me quickly say something about the Copan operator, because that came up earlier on. So what is true for the transfer operator is also true for the Copan operator. The spectrum of the Copan operator on L infinity, on which it's naturally defined, is not interesting. Again, it's the same phenomenon. If the map Tor is not invertible, then the spectrum of K is the unit disk. And if it's invertible, then it's a subset of the unit circle. And you can gain something by looking at the spectrum of the unit circle, but from where I come from, this is not such an exciting thing to do. Anyway, however, as I said earlier on, the Koopman operator is the dual operator of the transfer operator. So once you've found such a lovely Banach space H, a subset of L1, you can extend, using some functional analytic machinery, the Koopman operator K to the dual of H. This is then typically a much larger space. And it turns out on this much larger space, K is then compact and has discrete spectrum. And this discrete spectrum then coincides with the Ruelle resonances of the transfer operator. Okay, so the philosophy in the setup I'm going to consider is L is a nice object. You can make it even nicer if you restrict its domain to a smaller space. Once you've done that, you can extend the domain of the Kopan operator to a larger space, maybe to the dual, the topological dual of H. And then once this operator has been extended, it's also a nice operator. Okay, there's probably something that most of you know, but let me still make sure that we are singing from the same hymn sheet. Now, let me move on to go from this very, very broad view to a very, very narrow view. So in the following, and for the rest of the talk, I'm going to talk about analytic expanding circle maps. And what is an analytic expanding circle map? Well, it's simply a map from the unit circle T. So T is the set of all complex numbers, the modulus of which is equal to 1, the unit circle. And an analytic expanding circle map is a map which is analytic on the unit circle, and the derivative is bounded away from 1 on T. And if you want to have a concrete example in mind, you can't do much worse than thinking about z to the power p, where p is an integer with p greater than modulus of p greater than 1, for example, z squared, the doubling map. So this would be an archetypal example of an analytic expanding circle map. And in fact, later on, you'll see more examples. But for the moment, this is what you can think of if you want to think about an analytic expanding circle map. Now, just so you know that this transfer operator is actually a nice object. If tau is an analytic expanding circle map, then there's a formula for the transfer operator. So this follows simply from the change of variables formula by the definition of the transfer operator using the Copan operator. So if you have such an analytic expanding circle map, then it winds around the unit circle a certain number of times. Let's call it K. So this is the topological degree of the map. And this means that the map tau then has capital K inverse branches. And these inverse branches I denote by phi K. And the transfer operator is then a sum of these weighted composition operators. So for example, if tau is the doubling map, z squared, then phi of k would be square root or minus square root. And in this way, you can write down what this operator looks like. Okay, so the interesting observation about these analytic expanding circle maps is that the machinery that has been used to study expanding maps using thermodynamic formalism works as well. And here you can now see an example of one of these magic spaces I've been talking about. And once again, I apologize for the appearance of the slides. So this is probably I hope this is the worst slide you're going to see. Let me try and make sense of this. So I'm now going to explain, give you an example of a particular space H with a property that H is a nice subspace of the space of integrable functions on the unit circle, and has the property that when the transfer operator acts on the space, the transfer operator is compact. So this space is called H2AR for reasons that I'm going to explain in a second. And there is a parameter R in here. So R is a number between 0 and 1. And what we do is the following. We look at all L1 functions for which the Fourier coefficients decay exponentially, more or less. So how do we quantify that? Well, we say that a function f in L1 belongs to this magic space H2AR if this weighted sum of Fourier coefficients is finite, okay? So remember, R is a number between 0 and 1. So R to the -2 modulo of n is actually a number greater than 1. And if a function wants to satisfy this condition over here, it means that the Fourier coefficients of Fn have to decay exponentially, more or less at rates R to the power n, okay, more or less. So what does this mean? This means if the Fourier coefficients of a function, of an L1 function on the unit circle decay exponentially, then this means that the function must have an analytic extension. So these functions are actually analytic on an annulus around the unit circle. And this is why there's an AR floating around here. So AR is a reminder that these functions can actually be identified with functions that are analytic on the annulus of all complex number Z, the modulus of which is between R and R inverse, okay, 1 over R. So this is why this explains the appearance of this A over here. And these spaces are well studied. They have a place in harmonic analysis, and they are called Hardy spaces. Although Hardy himself had nothing to do with it, they were invented by the Riesz brothers. Anyway, so it turns out that, so this is the Hardy space of functions that are analytic on an annulus around the unit circle. And this space has a dual, and this dual is a very, very large space. And this is more or less, if you look at this, this is more or less the same. The definition is almost the same as the one before. The main difference is instead of R to the minus something, you have R to the plus something. So morally, what this is this is the space of all functions, whatever that means, for which the Fourier coefficients are allowed to decay, to grow exponentially at infinity. So these are highly singular objects. And how do you construct them? Well, here's one way of doing this. So you think of all, so you think about this space L1T, and then you define this funny norm. So this is a norm on the space on L1. But of course, the space is not complete. But what you then do is you complete this space. And the completion of L1 with respect to this crazy norm over here is this space H2ARC. There's a C over here. So this is a very, very large space. It contains all distributions, but even more. So in a sense, it's a space of hyperfunctions. And you can identify it with as the dual in a certain canonical way of this Hardy space. And why do these two spaces figure over here? Well, they come over here because it turns out that if tau is an analytic expanding circle map, then for all sufficiently small, for all R that are sufficiently close to 1, L leaves this Hardy space on the annulus AR invariant and turns out to be a compact operator. And similarly, by the duality I explained to you early on, K, the Copan operator, lifts to a compact operator on this huge space of hyperfunctions. And once again, as I said before, you can show that the spectra of the two operators, namely the restriction of L to this Hardy space and the lifting of K to this huge space of hyperfunctions, they have the same spectrum. And these spectral points are the Ruelle resonances. Okay, so this is the technical setup. So what you should have taken along from this discussion is for analytic expanding circle maps, there are candidates for spaces for which L and K make sense and are both compact and hence have nice spectral properties. Okay, so now we know what we're talking about. So the next thing I want to discuss is, now we talked a lot about spectra of these operators. Is there actually a way of calculating these spectra? And again, so calculating spectra of transfer operators has a comparatively long history. There are many, many ways of doing this. Here is a sort of a lumberjack method that is something that people would naturally use. And how does this work? So imagine you have an analytic expanding circle map, and then what you can do is you can use a Gaillaukin method to approximate the spectrum. So what do I mean by this? So you you take your favorite space of orthogonal functions. So there's something I haven't said, I swept under the carpet. So the space H2AR is actually a Hilbert space. So this is the thing that gives this away, is that there's a 2 floating around over here. So H2AR is actually a Hilbert space, and it turns out that the monomials z to the power n, a collection of all these monomials where n ranges over z, is actually an orthogonal, complete orthogonal system in this space. So this is why this space is quite nice, because the objects we know and love, namely the powers of z, they are an orthogonal system. And what we're now going to do is we're going to define a projection, Pn. This is the orthogonal projection in this space. I haven't really told you what the scalar product, what the inner product is over here, but it doesn't really matter. It is a bit like the one induced by L2 on the unit circle, but it has some weights attached to it. But it's not that important. At any rate, the powers of Z remain orthogonal in this space. And if, once again, R is close to 1, then you can look at these finite rank approximations of the transfer operator. So this would be a finite section of the operator, or a Gaillaukin approximation. So these are just different names for the same thing, of the operator L. So this is now essentially, this is a finite rank operator, and it has a matrix representation which you can easily write down. So the interesting thing about this matrix representation here is that it doesn't involve, it's essentially written in terms of the map Tor, so it's sort of related to the Koopman operator. Anyway, the message of this first line over here is simply you can write down the matrix that represents this finite rank operator, and it's simply this integral, this Fourier integral, if you wish, where the psi's are the powers of z and Tor is our map over here. Okay, so in principle, this is something you can calculate, and using the expansivity of the map Tor, you can show without much difficulty that these finite rank Gaillaukin approximants converge at exponential speed to the operator L in the norm of H2AR. So this is what I've written over here. You can show that you get exponential convergence in operator norm on this space H2AR. And the consequence of this is that you have an immediate consequence of this is that you have eigenvalue convergence. So in particular, you can show that the eigenvalues suitably reordered of the matrix LKJL converge to the eigenvalues of the true operator. And in particular, and I forgot to say at exponential speed. So once again, that's the same phenomenon. You have exponential speed over here. And in particular, you have no spurious eigenvalues. Every accumulation point of eigenvalues of the matrix is an eigenvalue of the true operator. And all the eigenvalues of L will be obtained in this way. So this is a truly good machinery to calculate the spectrum of the operator L on this space. Okay, so now in order to hone in on EDMD, let me say something about a class of benchmark systems. So ultimately, I'm going to say something about EDMD. So this is a method to calculate, a method that you can use to calculate the spectra of these operators. In order to gauge how well this method works, we need some benchmark systems for which the spectrum is actually known. So it turns out that for a particular class of systems, you can actually, the spectrum of the transfer operator is known explicitly. So let me briefly say something about this. What are these maps for which spectral data is known explicitly? So these are the famous Blaschke products. So what is a Blaschke product? A Blaschke product is an object of the following form. You take a number, let's call them K, of complex numbers in the unit disk. So what does that mean? These are all complex numbers, the modulus of which is strictly less than 1. And then you form this product over here and throw in a phase factor in front of it, so a complex number with modulus equal to 1, and hey, you get a Blaschke product, a finite Blaschke product. Before I say more about these Blaschke products, here are some pictures. So for example, if you take k equal to 2, and you choose a1 equal to 0, and a2 to be any of these 3 numbers, then here you get, and draw them by unwrapping the circle onto the unit interval, and this is what you get over here. So you get a variety of different, you get a collection of interval maps with 2 branches in this particular case that look that have various shapes. And the nice thing is that you can actually calculate the spectrum of the transfer operator arising from these Blaschke products. And before I do this, let me say something about these Blaschke products. So first of all, you can easily see that each Blaschke product is analytic on the closed unit disk. Well, this is simply because all these factors here are analytic on the closed unit disk. Next thing, each Blaschke product leaves the unit circle invariant. How do you see that? Well, this is a short calculation. You look at one of these factors over here, z minus ak, 1 minus ak bar z. And a short calculation shows that if z is on the unit circle, then so is this Blaschke factor, z minus ak, 1 minus a modulus of z. So this is a simple calculation. And if you then multiply them all together, you still get something that leaves the unit circle invariant. Now, in general, such a Blaschke product is not automatically expansive, but there are simple conditions. You can check simple conditions on these coefficients defining the Blaschke product that allow you to check whether the Blaschke product is actually expansive. And if it's expansive, this becomes important in a second. Then maybe this is something you are happy to believe. Then B has a unique attracting fixed point in the open disk. So why is that? Well, if B is expanding on the unit circle, it means that it must push points close to the unit circle away from the unit circle. So basically this means if B is expanding on the unit circle, it must be a contraction on the on compact subsets of the unit disk. And this means that it must have a unique attracting fixed point. So why does this unique attracting fixed point play a role here? Because it determines the spectrum of the transfer operator. So how is that? So imagine tau is an expanding finite Blaschke product. Turns out that the eigenvalues of the transfer operator on H2AR and also of the Kopan operator on H2ARC, the space of hyperfunctions, is given by the number 1, and all the powers of the derivative of the Blaschke product at the unique attracting fixed point in the unit disk and their complements. Okay, so here's a nice formula that allows you to calculate the spectrum of the transfer operator associated to an expanding finite Blaschke product. And this is good for us because if you want to check numerical routines, this is a class of systems where we can easily check how well our routines work. Okie doke. So now we know analytic expanding circle maps, we know their transfer operators, we know some crazy spaces on which they live, and we also have a class of examples of maps for which the spectra of the transfer operator and the Kopan operator, when considered on these crazy spaces, is well defined and is given exactly by these numbers over here. Okie doke. So now everything is fixed. I can move to the content of the talk. Namely, I'm going to talk about extending dynamic mode decomposition. So what is extended dynamic mode decomposition? Well, you could say it's a data-driven tool for model reduction. I don't really know what this means. I just thought I put it in because it sounds good. But well, it's not quite that. I racked my brain yesterday evening how I should describe EDMD, given that I don't know very much about EDMD, I have to confess. But the idea is the following. So what people want to do is you have a lot of data floating around. This data could, for example, be generated by a dynamical system. And then what you want to do is you want to find a simple description of this mass of data. And why would you want to do that? Well, maybe you want to forecast, or maybe you want to say something about dominant modes, or you want to say, so ultimately the goal is you want to find a simpler description of the complicated thing you have been given. So this is the idea of model reduction. You have something complicated and you want to somehow cut it down in some way to make it more amenable and still retain predictive power, for example. So this would be model reduction. And data-driven simply means that, well, it's like a machine that you throw stuff in, and then you turn a handle, and then you get something out. And then it's up to you to decide whether what you get out is actually useful for the purpose of model reduction. And this is something we wanted to see in practice. In our particular example, we wanted to understand, how does EDMD actually work? What does it tell you? What does it calculate? And for this, we try to use the objects we understand and love, namely these analytic expanding circle maps. So this is what the rest of the talk is going to be about. But before that, let me tell you more about this magic EDMD machine. So once again, here's the setup. Imagine you have some dynamical system. And in this case, by a dynamical system, I mean a discrete dynamical system. So you look at a state space X, curly X, and a map on this state space. And the EDMD algorithm then does the following thing. What you do is you choose a collection of observables. Let's call them psi k. So what are observables? Observables are simply phase space functions. So these are functions defined on the phase space X with values in the complex numbers or in the real numbers, depending upon your preferences. So you have a collection of n observables, and I collect them in a vector, psi1z, psi2z, and so forth. Okay, so this psi of z is actually a vector containing these n observables. And then we record the dynamics at certain state space points. Okay, so we choose m points in the state space X. Let's call them Z1, Z2, blah, 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 all the way up to Zm. And then we form the following two matrices, X and Y. So what is X? So more importantly, let's start with Y. So Y contains the vector of these observables. Then you let Tor loose on it, and you evaluate it at the point Z1 and so forth. So in a sense, here you get a collection of points, X and Y, data points that are generated by the map Tor. And the idea of the model reduction is then that you try to find a matrix that as closely fits this given data as possible. And if you want to define closeness, you have to commit to a measure of distance. And in this particular instance, we use the L2 norm on the data points. And the EDMD matrix, which is now an n times n matrix, is the n times n matrix A that minimizes the distance ax minus y, where x and y are these data points. Okay, so in a sense, this is sort of a least squares fit of the given data. Okay, so this is the idea behind it. So it's in this sense that it provides model reduction. And if you do things correctly, you can also calculate this minimum problem. So without going into the specifics of how you do this, if your observables and your points are chosen particularly nicely, then you can actually calculate this EDMD matrix as follows. It's given as the product of two matrices, G and H inverse. Well, what is H? H is the matrix you obtain by putting the observables together. You have psi k and psi l, and then you sum over the data points, over the m data points in this particular fashion. In this way, you get an n times n matrix HKL, and then you do the same thing, but you pop the tau into the first coordinate, and then you get a matrix G. And if you then calculate this object over here, this A is then the minimizer I have given on the previous page. Okay, so for us, this was the starting point for the EDMD algorithm. And our question was, well, this is some matrix. And obviously, this is something you do with the dynamics. What do the eigenvalues of A have in common with the Ruelle resonances of a given system? And for analytic expanding circle maps, we soon realized, so this is something that was published last year, that if you commit to a particular choice, for example, if you choose your psi k, the observables, to be powers of z again, because we're talking about circle maps, and you choose your points z, m to be equidistant spaced points on the unit circle, then you get convergence in the following sense. So it turns out, this is not that difficult to see, this matrix G over here approximates the matrix L that we had on the slides earlier on. And L in turn is a matrix representation of the Sky-Jokin projection of the transfer operator. And as a result, we argued that the eigenvalues of the transfer operator on H2AR are approximated by those of A, the exponential speed in n, provided that m is chosen large enough. So the moral here is that n is, if you wish, primary, m is secondary. The game you play is you choose your level of observation, you choose your n observations, and then you crank up your m, make it very, very large. And if you do this in particular sets, in this particular setup, you obtain convergence. This is also something you see when you do numerical experiments. So we weren't particularly satisfied with this, and the main question I'm now going to address is, what's the relation between n and m? So for the rest of the talk, I'm going to talk about numerical experiments using this EDMD algorithm applied to analytic expanding circle maps using these formulae over here. Okie doke. So here are some pictures. So here are numerical results using our benchmark maps, our Blaschke products tau. So here we've chosen Blaschke product of degree 2. So this corresponds to, if you unwrap it, this is a map with 2 branches on the unwrapped unit interval. And we chose mu to be a particular number. Well, for all of the discussion that is going to follow, we chose the parameter over here to be -1/3 times a little phase factor over here. And you may well wonder, why did we choose this particular mu? Well, because it gives pretty pictures. So this is always the privilege of the numerical analyst, that you choose parameters in such a way they get pretty pictures. And these pictures are designed to to illustrate the various convergence results relative to n and m. So the first thing we're going to do is we keep n fixed and assume that n is very, very large. And we do this in 2 particular fashions. These gray dots over here are instances where we chose the phase space points to be equally spaced points on the unit circle. And the crosses are obtained from a time series. So instead of choosing the sets equally spaced, you can also have them generated by the dynamics of your system. So you take an arbitrary starting point and then you iterate the map m times, and then you get a collection of m points, and you can also use them for the EDMD recipe. And these pictures illustrate the relative merits of the convergence of what happens over here. So here, for the first picture, n, the number of observables, is fixed to 11. And we have cranked up m to quasi-infinity. So m is very, very large. For equidistant points, large means 100 points. And if you use trajectory points, so if you use a time series, then 10 to the power 4 is infinity. And you can see this over here. The circles over here are the exact values obtained from the fixed points of the multiplier of the fixed point of tau. Actually, I saw that sometimes I see people trying to ask questions. Were there any questions so far? I'm going like a bulldozer over this. There was seemed to be one question, or maybe I'm wrong.
Yeah, there's a question on the chat, but
yeah, sorry, I tried to monitor the chat, but
no, it's okay.
I wasn't particularly effective at monitoring it.
No, I think it's better if you just continue, and then we'll have a Q&A at the end. Yeah.
Yeah, let me try. Actually, I put the chat up specifically for that.
Ah, okay. Yes, there's a question. Z is complex.
Yes. Is Z complex? Yes, that's a very good question. It is. And let me put. Oh yeah, here we go. Now I suddenly see the amazing. Maybe I should move this away. Sorry about this. Yes, Paulina asks, is it complex? Yes. The answer is yes. And let me try and move this away. Okay. Yeah, sorry about this. So next time you need to shout a bit louder. Sorry about this. Okay. So Z is complex here because we are looking at the map on the unit circle. Let me try and get, okay, here we go. So what you can see over here is that the convergence of this algorithm is essentially determined by n in this particular submap. The larger n is, here n is 11, and you can see the first 3 circles are filled, you have hit the true eigenvalues, and the rest is somehow hasn't converged yet. So open circles mean that this guy should actually be here, but it is not. So here, this means that the first 5 eigenvalues obtained via EDMD, either via equidistant points or time series points, have perfectly converged. The rest is not very good. If you then crank up n, so the number of observables, then you see that more points are actually filled. So this illustrates that if you choose m large enough, then the convergence is essentially determined by the number of observables. Okay, good. Here is a slightly different picture illustrating the same result. So what I've used over here is, here I've plotted the absolute error of the first 5 subleading eigenvalue pairs using EDMD with 1,000 equally spaced nodes. So m is fixed over here, and here I crank up n. So the number of nodes is fixed, but I crank up the number of observables. And so down here, n is the number of observables. And on the abscissa, we have the absolute error going down all the way to 10 to the minus 16 on a logarithmic scale. And here you can see that all these errors decay exponentially at the same rate. So we have lovely exponential convergence of the EDMD matrix eigenvalues to the true eigenvalues of the transfer operator.
I have a small question.
Yes.
Just maybe relevant. In which sense it is model reduction? Because what you show us, you take a simple one-dimensional map and you model it by multiplication to a matrix like 1,000 by multiplication in very high dimensional space. Yes. In which sense it's model reduction? To me, it's model explosion.
Well, because the one object is infinite dimensional, and the object we have here is finite dimensional. So
yeah, but we start with finite
model
dimension.
from infinite dimensions to finite dimensions.
Yeah, but we start with finite dimensional with a one-dimensional map.
No,
and then we model it by something infinite dimensional.
No. The model is that we have a probabilistic description of the map. So we're not looking at the map, we are looking at an operator associated to
okay, good.
Which is a truly infinite dimensional object.
I see, okay, I got it.
Yeah, in that sense.
Okay.
Does it make sense?
Yeah, so just
okay, okay.
philosophy.
Yeah,
thank you.
Okay. Okie doke. Numerical results illustrating that if you choose M large, then the convergence of the algorithm is determined by N, and it's exponential in N. The errors, the absolute errors, decrease exponentially fast in N. Okay, so now let's try and quickly talk about the relationship between M and N. So in practice, you don't always want to, you don't know what infinity means for M. In practice, you want to know how large do you have to choose M given an N? How many phase space points do you have to choose given that you've committed to a number of observables? And if you do this in an incorrect way, you get rubbish. And this is what I'm illustrating over here. So here I've chosen EDMD with a small number of M. So we take 22 equidistant points or trajectory points. And here we choose 11 observables, and here we choose 21 observables. And once again, we compare the eigenvalues of the EDMD matrix with the true eigenvalues. And so remember, the true eigenvalues are the hollow circles, and the EDMD eigenvalues are the gray dots over here. So here you can see that the gray dots, in this case, they are, well, sort of, they are close to the, so you get the first eigenvalue 1, and the subleading eigenvalues are well approximated, but then you get rubbish. This is for equidistant. And time series is even worse. So here you have got these crosses. So in principle, you should have 11 such crosses over here, but the crosses are miles away from where they should be. So you can't even see them because they're outside this square over here. So this in particular means that time series based EDMD for this, in this particular setup where M is equal to 22 and N is equal to 11 fails miserably at approximating the true spectrum of the operator. And it's even worse if you crank N up. So we keep M equal to 22 fixed, and we choose N equal to 21. And then you can see that neither equidistant EDMD nor time series EDMD give you anything that resembles the true spectrum, apart from the eigenvalue 1, which is detected in any case. Okay, so the moral of this is here is the following: trajectory-based time series approach fails miserably in the setup. Equidistant chosen phase space points M. If you choose M equal to N, you fail. This is this case over here. If you choose M is equal to 2N, you do slightly better. So maybe there is something, if you choose M to be a small integer multiple of N, you are in good shape. And it turns out that this is actually the case. So we can actually prove that you obtain convergence if you choose M to be a small integer multiple of N. Before I show you the result, here's another picture where you can see this. So what does this picture show you? So here we plot M, the number of phase space points, and N, which should be a capital N, the number of observables. And what is approximated here is the subleading eigenvalue. So J should actually be equal to 2, and this N should be a capital N. So we are looking at the absolute error of the subleading eigenvalue for our fixed Blaschgren product we have been using all the time. And what you can see in this picture is how the error of approximation varies as you walk along, as you, for example, if you fix an M and then crank up your n, you can see that your approximation gets better and better, but then you improve your n, it gets worse again, okay? So this is when you walk along over here. So if you fix your number of observables and then crank up m, what you observe is that the approximation gets better for a while, and then it gets worse again. And this is illustrated by these colors. The colors are actually showing you the absolute error over here. And it looks if there was something, if these were steps, they're not steps, it's actually continuous. This is actually a slope. It's just that our rendering of the colors is stepwise. This is why it looks as if we had steps over here. And likewise, if you choose, if you fix your n and you crank m up, so actually I explained it the wrong way around earlier on. I do apologize. I mixed up n and m. So maybe try this again, although I'm running out of time. So, so the moral of this is that if you choose m to be a fixed multiple of n, you get nice convergence. In this particular setup, if you choose m to be 5 times n, you get nice exponential convergence. And it looks as if there was some something to prove over here. And this is the final penultimate slide. I'm going to show you a result that actually establishes how you have to choose m relative to n in order to achieve convergence. So suppose we have an analytic expanding and orientation preserving circle map. The orientation preserving doesn't really matter. This is just for the parameters that I'm going to explain to you, which are easier if I fix this particular scenario. So for a particular expanding circle map, there are 3 radii, R3, R2, R1, all sandwiched between 0 and 1, and ordered according to these inequalities over here. And the meanings of these radii are the following. If you let tau loose on all complex numbers on the circle of radius R1, then they are sandwiched between R3 and R2. So roughly speaking, what this means is that R2 is the minimum complex expansion on the unit, on the circle with radius R1, and R3 is the maximum complex expansion. Here's a picture illustrating this. So once again, this is the dotted line over here is the unit circle. My R1 over here is a circle of radius R1. And then what I do is I let my map tau loose on this circle of radius R1. Then what I get is this green curve. It winds around twice because I'm looking at the Blaschke product of degree 2 in this for this picture. It can be more, but I want to choose my radii R2 and R3 in such a way that R2 snugly fits outside this image, the green curve, and R3 sits snugly from inside along this green curve. So once again, the idea is that given R1, R2 represents the minimum expansion, and R3 represents the maximum expansion that tau exhibits on this circle of radius R1. And with this in mind, with this notation fixed, we can prove the following result. So imagine you have an analytic expanding circle map, and you fix these 3 radii. Then you can show that the Copan operator is Hilbert-Schmidt on this funny space of hyperfunctions. And you can estimate the distance in Hilbert-Schmidt norm of an operator which the matrix representation of which is the EDMD matrix. And you can actually estimate the distance of the true Copan operator to its EDMD approximation using these 3 quantities, R1, R2, and R3. And if you then commit to choosing a number d equal to this expression over here, the logarithm of R2 times R3 divided by the logarithm of R1, and then take the ceiling function, then if you then choose m equal to d times n, that is, if for every step in your calculation of the EDMD matrix, you always take d times as many equidistantly spaced points as you have observables, then you obtain exponential spectral convergence of the eigenvalues of the EDMD matrix in the size of the matrix N over here. Right, so this is the content of this theorem. Maybe since I'm running out of time already, I'm already 5 minutes over, I stop.
It's okay, I mean, you can continue. No, you can continue if you want.
No, I mean, it's my last slide anyway. I mean, the last thing would be to tell you how the proof works, but this is usually the stuff that people are least interested in, so I'm better going to stop here. Thank you very much for your attention, and apologies for running over the allocated time. Thank you very much.
All right, yeah, thanks a lot. Thank you very much for the nice talk. Any questions?
So I would have a question.
Yes.
So in proving this, do you use the fact that the entries of capital G are actually a trapezoidal rule approximation of the entries of capital L?
Yes, exactly. So this is you are exactly right. You spotted how it works. This is an extremely simple-minded proof, and this is exactly how you do it. So you show that the G's converge at exponential speed entry-wise to L. And this is why we use the Hilbert-Schmidt norm, because it just gives you a simple expression for this. But it's a very lumberjack type argument. But it gives you, curiously enough, it gives you the right results, which by the picture that I didn't explain particularly well, turn out to be sharp. But this is exactly what is happening.
Okay, thanks.
I do have a question. Can you hear me?
Yes.
Okay, great. I have two questions actually. The first question is about the example that you showed us for Blaschke product.
Yes.
Which observables you chose? So the function psi, I didn't get.
Oh, sorry. Yeah, this was sort of it's buried over here. So our observables are always
the polynomials. Okay, I see.
It's always polynomials. Yes.
Sure. And the second one is, in the beginning, you made this more precise in terms of the R. You should choose the R in this definition of the space A2 AR. R should be close to 1. So yes. Why is that the case?
Well, in the first instance, because the map Tor is only assumed to be analytic on the unit circle. And somehow for these spaces, you want that the sort of what enters the construction of these spaces is the region around the unit circle around which Tor is analytic. So Tor may not be an entire function. It may only be analytic around a small neighborhood of the unit circle. And that already restricts the allowed choices for R.
I see.
So you can't choose any R. You always have to choose R close to 1. But if you want to, if you give me a particular circle map and put a gun to my head, then I'd be happy to come up with an R that works.
Perfect.
And maybe even without a gun.
Perfect. Okay. Thank you so much.
Yeah, Paulina, do you have a question?
Yeah, Paulina, sorry.
Yeah, I just wanted to ask the following. So when you choose the points on the unit circle, which
yes.
You choose them equidistributed.
Yes.
So I was wondering whether the result depends on where particularly you choose them. By this, I mean that, for example, if you just rotate all of them by an angle, like, I don't know, choose m points and don't put the one at 0, put the first one at pi over 25, for example, and so don't put the point at 0 at all, for example, would you get better approximation?
No, for our, I mean, the theorem is actually formulated for arbitrary rotations of your. So we don't, at this level, we don't see anything. So the theorem remains exactly the same, even if you.
So, but no, I meant when you mentioned at some point that you get that you need to choose your N capital and M capital very carefully.
Yes.
So yes, so that I was wondering whether this can be remedied just by rotating the M points rather than adjusting them.
No, you have to increase the number of points. Just rotating them doesn't work. I mean, ultimately, you're talking about a numerical integration. If you do numerical integration, it doesn't help you if you just rotate your collocation points. You need to take more of them to get a better result.
Okay, so you just no, but yes, I understand that you have to get more of them. But the question is whether you still need this relation to hold. So I missed a little bit. What is your condition? What is your connection between M capital and N capital?
So the result is that for a particular expanding circle map, you can calculate a number D, where D essentially is more or less the arithmetic mean of the minimum expansion on the unit circle and the maximum expansion of the unit circle. So this is your number D. And if you then always choose the number of collocation points M to be a fixed multiple D, that D I just explained, times the number of observables, then you get exponential convergence in N.
So you need a specific connection between the number of observables and the number of collocation points.
Yes, exactly. And as I try to illustrate, if you don't do that, if you choose M and N in an arbitrary fashion, there's no guarantee that you get convergence.
Yeah. So my question was more or less whether you really need this connection, or this can be remedied by choosing different, just by rotating the collocation points.
No, I don't think so. No.
No. Okay. Good. Sure. That was the question. Thank you.
Okay. Good.
Yeah, I have a question out of your talk, and this is, are you going to look at pseudo-differential operators?
Not really, because I know precisely nothing about pseudo-differential operators. I'm sorry.
Because the reason is that they could be very, very powerful.
In what sense?
So you may want to, maybe. And the other question is curiosity. Is your co-author first name is Alexei?
My co-authors are Wolfram Jutz.
Slipanchuk.
No, it's Julia Slipanchuk. She's in
it's Julia. Okay.
Yeah, Julia.
That helps me.
Not Alex Slipanchuk. I didn't know that.
You know that person, right?
I know Julia, but not Alex.
You don't know Alex. Okay, cool.
No. So
I know Alex. I didn't know Julia. So we're perfect now.
Who is Alex?
Well, he's a fellow who studied statistics in Canada.
Right. Okay.
And I think he's now at UC College. And I think also that he's interesting in, as everybody else, in AI and data science.
Right, okay.
But I didn't know he knows anything about dynamical systems. So that's my curiosity.
Okay. No, sorry, I didn't
know. Anecdotal for the fun. Thank you very much for your talk.
Well, thank you very much for listening. So Martin?
Yeah, Martin.
Thank you very much, Oscar. That was very enjoyable. Do you know how much of that could be carried over to a higher dimensional mapping? Or how much of that is linked to the fact that the mapping itself was on a circle or on a one-dimensional domain? No,
so in principle, if you take the dimension is not that important. What is important is expansiveness and analyticity. Analyticity we can also relax, so we can prove the same result for maps of lower regularity, but expansion is important. So for example, the same result can be proved for expanding maps on t to the power n, so on the multi-torus, I suppose.
Okay.
So that's not important. Expansiveness is important.
Okay. Thank you very much.
we try to do this, something like this for hyperbolic maps as well. So maps where you have not just expansion, but also contraction. And there's a possibility that for a particular Anosov diffeomorphisms, we can do the same argument. But again, you need hyperbolicity is absolutely essential for this to work. Without that, there's no hope. So all these situations where people really want to use EDMD we can't say anything about, because we need to have very, very specific spectral properties of the transfer operators. And these are only available for a fairly narrow class of systems at the moment.
Okay, thank you very much.
Any other questions? Yeah, all right, then, since there is no further questions, so let's thank the speaker again. Thanks, Oscar, for everything.
Well, thank you very much.
Thank you.
Thanks very much for coming.
Yeah, thank you.
Good, excellent. I like
I
you.
think so. Someone is very excited. Yeah, all right. All right, so have a nice end of the day, and then see you soon. Yeah, all right, bye-bye.